Assalamualaikum warahmatullahi wabarakatuh, and very good day to all of you. So today we will start with our first lesson. So we will discuss about chapter number 1. So under this chapter we will discuss about the concept definitions and also the basic principle in thermodynamic 1. In terms of contents in chapter number 1, first we will discuss about an introduction of thermodynamics. Okay, number 2 we discuss about the system, properties and also processes. Number 3 and number 4 we will discuss about the device that we use to measure the pressure, which are manometer and also the barometer. And the last one we will discuss about the technique in order to solve the problem involved with thermodynamics. Introduction of thermodynamics. Okay, first we need to know what is the meaning of thermodynamics. Okay, in terms of definition. Okay, thermodynamics actually in terms of the wording or the words of thermodynamics actually consists of two main words, which is first thermo parts and also the dynamic parts. Okay, so actually these words actually come from the Greek words, which is thermo actually come from therme, which means heat, and dynamics actually come from dynamis in Greek, and the meaning of the dynamis is power. So now thermodynamics actually is the heat power in terms of the meaning of the words. Okay, so in terms of definition, thermodynamics actually is a basic science that deal with energy. Okay, for example, we have here in the figures, we have a piston cylinder device linked with a tire. So when we supply heat to the cylinder, so the piston will move, and the movement of the piston will produce power, and this work or power or energy will rotate the tire, and this system will move forward. Okay, so this is an example of a thermodynamic system, which is the system will involve with heat and also power. Okay, so any system that involve heat and then produce power or work, we consider the system as the thermodynamic system. Okay, in terms of approaches in thermodynamics, so these approaches we will use in order to explain or to analyze any thermodynamic system that we will learn in this thermodynamic 1. There are two types of approaches. First we call the classical approach, and the second one is statistical approach. Okay, so for classical approach, this approach actually is the macroscopic approach, where in terms of explanation, so this approach does not require a knowledge of the behavior of individual particle. Okay, for example, if you want to analyze the pressure in a container, okay, so the pressure actually comes from the particle momentum to the wall, the interaction of gas particle or fluid particle momentum to the wall of the container. Okay, so the red color circle represent the particle. Okay, however, for the macroscopic approach, we will not go into detail about the behavior of the individual particle in order to determine the pressure. What we will do, we just put the pressure sensor or pressure gauge to the container. So by using the device, we will have the pressure. So we just use the pressure gauge to measure the pressure, and no need to know the particle behavior in order to determine the pressure. So this is the macroscopic approach. However, for the statistical approach, this approach actually is the microscopic approach, which means The approach actually is based on the average behavior of the large group of individual particle, which means we need to know the behavior of the particle if you want to use this approach, statistical approach or the microscopy approach. Okay, for example, let's say we want to know a flow direction of gases with different density. Okay, let's say we have the first type of what I call gas that represented by the red color circle. So we want to know how the other gas flow within the tank. Okay, so in order to know, so we need to know the behavior of the gases with different density. Okay, for example, the blue color circle represent the other type of gases with different density. Okay, by knowing the behavior, we will know how the other gases flow in the container or in the tank. So we need to know the behavior of different type of particle in order to make the conclusion or to make the analysis of the mixture of the gases in the tank or in the container. Okay, so that's what we call the different in terms of approaches between the classical and also the statistical approach. Okay, however, throughout this subject, thermodynamics 1, we will use the first approach, which is the classical approach. So no need to consider in detail the behavior of the different group of particle inside the system. Okay, so this is another example, the difference between the macroscopic and also the microscopic approach. Okay, for example, we have a tank located on a trolley. So let's say the trolley moves with velocity of v system, and the height of the trolley or the height of the system is z. Okay, so this is our system, and this is considered as macroscopic example, where from the velocity and also from the height of the trolley we can determine the kinetic energy and also the potential energy of the whole system. Okay, so this approach we consider as the macroscopic approach. Okay, we can determine a kinetic energy for the whole system and also the potential energy for the whole system. However, if we consider the particle movement inside the tank, where we have velocity of the molecule or particle, and when we consider what we call the behavior of the particle, so this approach we consider as the microscopic approach, where from the value of velocity of the particle or of the molecule, okay, and also the height of the particle relatively to the what we call the bottom surface of the tank and so on, so we can determine the kinetic energy of the particle and also the potential energy of the individual molecule or particle. So this approach we consider as microscopic approach example. Okay, so that's the difference between macroscopic and also microscopic. Okay, now it's about the thermodynamics principles that we will use to discuss about any thermodynamic system in this subject. First, we have the first law of thermodynamics. So this law actually the conservation of energy principle that you have learned before, where this law mentioned that energy can change from one form to another, but the total amount of energy remain constant. Okay, for example, as we look in the figures, so we have a cyclist cycling down a hill, where we have three positions of the condition of the cyclist. First, we have the condition of the cyclist at the top, at the middle, and at the bottom of the hill. Okay, so PE stand for potential energy, KE stand for kinetic energy. So the formula for PE, potential energy, is equal to mgz, and the formula for kinetic energy KE equal to half multiplied by mass multiplied by velocity of the cyclist, power of 2. So at the beginning of the initial state of the cyclist, the height of the initial state will be Z. Okay, if we base on the first law of thermodynamics, the total amount of potential energy at the initial state at the top of the hill will be equal to the kinetic energy at the final state, which is at the bottom of the hill. So this is what I call the implementation of the first law of thermodynamics. So if you look at the top of the hill, because no velocity yet, so we have the maximum of potential energy value, which is, let's say, 50 kilojoule, and the kinetic energy value will be 0 because no velocity of the cyclist. Okay, so when the cyclist I call cycling down the hill, so at the middle, let's say at the middle of the journey of his journey, so we'll have the combination of potential energy and also the kinetic energy. Let's say potential energy 25 kilojoule, kinetic energy also 25 kilojoule. So in total, still we will have 50 kilojoule based on the first law of thermodynamics. Okay, at the final state at the bottom what I call of the hill, we can see that the kinetic energy will be maximum at 50 kilojoule and the potential energy will be 0 kilojoule because the height of the the cyclist will already 0, because the formula for PE equal to mgz, so Z equal to 0. So at the final state, the energy, the potential energy of the cyclist will be 0 kilojoule. But still, if we implement the if we refer to the first law of thermodynamics, in total PE plus KE still equal to 50 kilojoule. So this is the basic concept of the first law of thermodynamics. Okay, the second law that we normally use in thermodynamics is the second law of thermodynamics. So this law actually involves with the what I call the energy quality. So this law mentioned that energy has quality and also quantity. So this law, the second law of thermodynamics, explains that the actual processes occur in the direction of decreasing quality of energy. Okay, for example, so we have a cup of coffee. At the beginning, the temperature is 50 degrees Celsius. Okay, so naturally, after a period of time, so this coffee will cooling down to 25 degrees Celsius due to the heat rejection to the surrounding. Okay, so this process naturally occurs. So the energy decrease throughout the process where the heat release. So the the quality of the energy decrease, okay, throughout the process. However, if we base on the second law of thermodynamics, the second photo will not happen. So in nature, this process cannot happen because in the second figures, what call the temperature, let's say the initial temperature 25 degrees Celsius, it is impossible to increase the temperature of the coffee inside the cup to the 50 degrees Celsius without using any additional system. Okay, so the second case cannot happen in nature. So this considered as the example of the second law of thermodynamics. Okay, because the actual process occur in the direction of decreasing quality of energy, not increasing quality of energy. Okay, so for the first case where we have the reduction of the temperature, naturally refer to the decreasing quality of energy. However, the second case where we have what I call the increase of temperature, which is this is impossible. So the second case actually refer to the a direction of increasing the quality of energy. So this will not happen if we refer to the second law of thermodynamics. Okay, now about the application of thermodynamics. So now I will show you where we will apply the concept of thermodynamics in actual life. Okay, so first we will implement a lot of thermodynamic principle in the power plant operation. Okay, where this is the basic or the simple schematic diagram of the part of the power plant schematic diagram, where the power plant will involve is what we call the boiler and also the turbine. So the heat that's supplied to the turbine will produce energy, where this energy will run the turbine to produce power. Okay, so the second application is in the internal combustion engine, as shown in the figure. Okay, and this figure show the schematic diagram of this cross section of the engine, the cylinder of the engine. Okay, where we have the chemical reaction inside the cylinder of the engine to produce heat, and this heat will produce power that push the piston what I call upward and also downward in order to rotate the tire of the vehicle. Okay, the third application is at the refrigeration and also at the air conditioning system. Okay, where for this system we need to supply power to the compressor, and from the system we need to absorb heat and also release heat in order to reduce the temperature what I call of the confined space for the refrigeration system and also for the air conditioning system. So these are four main application of thermodynamics. Okay, so we will learn into detail about the system when we learn thermodynamics 2. Okay, dimension and units that used in thermodynamics. Okay, so for dimension, dimension actually the names that characterize the physical quantities. Okay, so we have 7 primary dimensions. So probably you already learned these things in your what I call secondary school. So we have 7 primary dimensions. So we have length, symbol L, mass, time. Okay, so we have length with symbol L, mass with symbol M, small letter m, times T, small letter t, temperature, capital letter T, electric currents, capital letter I, amount of light, capital letter of C, and also the last one is amount of matter, the capital letter of N. Okay, so these are the primary dimension that we normally use in our call engineering subject. And then we have the secondary, or we call derived dimension. For example, we have velocity V, energy E, force F, and so on. Okay, so for example, we have a tire. Let's say the mass of the tire is 10 kilogram. So the tire rotate at velocity V. Okay, so this tire will stop at certain distance. Let's say the length or the distance is L equal to 100 meter, and we measure the time from the initial state to the final state condition of the tire. Let's say the time is 10 seconds. So M, mass of 10 kilogram, is the primary we consider as the primary dimension, length also primary dimension, time also the primary dimension. However, for the velocity we consider as the secondary we call a dimension, because the parameter is actually, or the parameter or dimension actually come from the combination of different primary dimension, where we have the formula for velocity equal to length, distance divided by time, which is, if we calculate based on the data given, so we'll have 10 meter per second in terms of velocity of the tire. So this the example just want to show the difference between the primary dimension and also the secondary dimension. Okay, so in terms of unit, so the unit in terms of the definition is the magnitude assigned to the dimension. So we have dimension, and also we will have a unit for the dimension. Okay, so we have two type of unit. First, we have the international unit, normally we refer as SI unit. The second one is the English unit, USC. So normally what call USC is the United States Conversion, I think United States Conversion Unit. Okay, please check this one. And so normally in US we'll use English unit, okay, for the measurement and also the calculation. Okay, so for the primary dimension, so we have 7 primary dimension as mentioned before: length, mass, time, temperature, electric current, amount of light, also amount of matter. So the SI unit for length is meter, for mass is kilogram, kg, for time second, temperature Kelvin, we will use Kelvin, electric current we will use ampere, amount of light we will use candela, CD, and amount of matter we will use mole in terms of SI unit. However, for the English unit, for length we will use feet, mass pound mass lbm, time the unit for SI and also English we will use the same unit, second, and the temperature we will use Rankine R for the English unit. Okay, so in terms of conversion, if we want to convert for example from the English unit to SI unit, so we will have specific value we need to consider. For example, 1 feet equal to 0.3048 meter, 1 pound mass 1 lbm equal to 0.45359 kilogram. For example, the temperature 1 Kelvin equal to 1.8 Rankine, and so on. Okay, so these are the unit and also the conversion for the primary dimension. However, for the secondary dimensions, so these are the example, just the example. For example, we have force. The formula will be equal to F equal to ma, energy E, weight W equal to mg. So we have pressure and also velocity. So these are the example of secondary dimension. So the unit for each secondary dimension I mentioned that I just mentioned here. For force, the unit will be Newton, kilogram, Newton. So actually the unit the Newton unit actually is equal to kilogram meter divided by second square. Energy, the unit we will use for the energy is joule, weight Newton, pressure we will use Pascal, and the velocity we will use meter per second. Okay, so in terms of English unit, for force, English unit will use lbf, which is pound force. Okay, and energy will use btu, weight lbm, feet divided by second square. Pressure, English unit will use atm, and velocity, the English unit will use a feet per second. So in terms of conversion, for force, 1 lb force is to 4.45 Newton. However, for the energy, 1 BTU equal to 1.0551 kilojoule, and for the pressure, 1 atm equal to 1 atm equal to 101 0.325. So these are the SI unit, English unit, and also conversion for the secondary dimensions. Okay, so about the prefix in SI unit. Prefix means normally we will use for the number, the big number, or for the a huge number of dimension, or certain dimension, or the very small value of specific dimension. Okay, so we can use prefix to simplify or to shorten the numbers of the individual dimension. For example, we can use tera, mega, kilo, centi, milli, micro, nano. Okay, where tera is 10 power of 9, mega 10 power of 6, kilo 10 power of 3, centi 10 power of negative 2, milli is equal to 10 power of negative 3, micro 10 power of negative 6, nano 10 power of negative 9. We use this prefix in SI unit in order to shorten the numbers of specific dimension. And remember that in terms of dimensional homogeneity, so we need to know that if we have a specific formula, so we need to make sure that so every term in an equation must have the same unit. Okay, for example, we have z equal to a plus b, for example. Okay, so the unit of z must be equal to the unit of a and also the unit of b, otherwise the equation will be wrong.